Okay, next we talk about equivalence relations on groups, and this will be fundamental for a lot of stuff that comes in the next weeks. So here's one of the most important equivalence relations whenever I have a subgroup in a group G. I define A to be in relation to B if and only if A dot B inverse, I leave out the dot, is an element of H. And we have to show that this is an equivalence relation. So is it true that A is equivalent to itself or in relation to itself? Well, yes, because then this here becomes A dot A inverse, which is the identity, and the identity must be an element of H because H is a subgroup. This is important. If H were merely a subset, this would not have to be true. So reflexivity could fail already. So if you hand this in as a solution to an exercise, please write down here because H is a subgroup. So to show symmetry, we assume that A is equivalent to B or in relation to B, meaning that A B inverse is an element of H, and we have to show that then automatically B is in relation to A. So we take a look at B A inverse. Why would this be in H? This is the first time where we actually need an idea. So we write B as the inverse of B inverse. We proved long ago that this is always true. And now remember the formula for the inverse of a product of two group elements. This turns around the order and takes the inverse of each of the factors. This was proposition, I think it was proposition 1, was the first proposition we proved. So take a look at that. By the formula of the inverse for the product, this would be this factor, B inverse inverse, which we have here, times A inverse. So this is exactly the formula for the inverse of a product. But now AB inverse is an element of H by assumption. And now again, because H is a subgroup, the inverse of this element must also be an element of H. So again, because H is a subgroup. Otherwise, this does not need to hold. So we assume those here hold. A is in relation to B, B in relation to C. This means exactly this by definition. And we have to show that then AC inverse is again an element of H. Now if you did the exercises of the last few weeks, maybe you are used to trickery like that. We insert the identity here because we need the B somehow. By associativity, I do not need to worry about parentheses, so I can write it like that. And now this identity can be written as B inverse times B times C inverse. Again, associativity, so no need to worry about parentheses. And now by assumption, both of those elements lie in H. So again, because H is a subgroup, this product lies in H, showing that actually A is equivalent to C. And again, you need to write down H is a subgroup. So finally, we're supposed to take a look at the equivalence class of the identity. By definition, it contains all the elements of G that are equivalent to E. So this would mean that B E inverse lies in H, but of course E inverse is E, and E doesn't change anything, so this is simply the condition to be in H. So the equivalence class of the identity is simply the subgroup H, which is a subset of G. Of course, it's also a subgroup, but here is important I want to stress the fact that this here, the equivalence class, is a subset of the whole set. And we will work with this equivalence relations a lot in the future. So I hope you really try to do this exercise, or at least that you could follow all the steps here. Okay, next equivalence relation on a group. We say that A is equivalent to B, or in relation to B. We are yet to show that this is equivalence relation if there exists an element of G such that A can be written as X, B, X inverse. This seems a bit random at first, but this is a very important operation on groups called conjugation, and we will hear about that a lot more in the future. Okay, as always, reflexivity is easy. A can be written as E dot A dot E inverse. So if I choose X to be E, then this shows that A is in relation to itself. So next, symmetry. We assume A is in relation to B, meaning that A can be written like that for some element of the group. But now if I multiply with X inverse, which exists because we are in a group, from the left, I get this. Again, associativity, blah, blah, blah. We come to a point where we can start to leave these arguments out because they are always the same. And then again, I multiply from the right with X itself, and I end up again with this because X inverse X using associativity gives me the identity, which leaves B unchanged. So I end up with this here. And as always, multiplying by a group element from the left or the right is a map from G into itself. So if these are the same, then the image under this map is the same. So this equality holds. And to go in the other direction, you simply multiply by the inverse element. So this shows B can be written as X inverse AX, which is nothing but we need this form. So if I define Y to be the inverse of X, then this here is Y, and Y inverse is X inverse inverse, so X. So this is indeed of this form for some group element. So this shows that B is in relation to A, proving symmetry. Finally, transitivity. So we assume that A is in relation to B, B in relation to C, meaning exactly this for some group elements X and Y by definition. And then we have to conclude that A is in relation to C. So we need some element heart of this group such that A can be written like that, where the C is in the middle. So let's try that. This is not too hard because A can be written like that by definition. And now we plug in that B is Y, C, Y inverse, X inverse. Again, associativity, I don't care about the parentheses, except for now, where I deliberately put them here. And again, remember the formula for the inverse of the product. This is not Yx inverse, but Xy inverse. I have to switch X and Y around. And now we have it. Heart is exactly Xy. And this is an element of G because G is a group, and this shows transitivity. So this here shows that A is in relation to C. So conjugation is actually an equivalence relation on this group. So finally, we have to take a look at the equivalence class of the identity. By definition, this class consists of all elements of G that are related or equivalent to E. By definition, this means B can be written as X, E, X inverse for some group element X. But here I can forget about the e, so I end up with x inverse, which is always e. So here in this case, the equivalence class is the trivial subset of G consisting only of the identity. And again, we're going to hear a lot more about conjugation as this course here progresses. Okay, now for part C. Parts A and B are standard equivalence relations on groups. This here I found in Pinter's delightful little book. We define A to be equivalent to E if and only if the product AB inverse commutes with every element of the group. This, of course, is just interesting for non-abelian groups, because otherwise, trivially, this element commutes with all the other elements, so there is no information in this equivalence relation. So let's check if it's indeed an equivalence relation. So, as always, reflexivity is easy. A is equivalent or related to A because A inverse is the identity, and this commutes with every element of the group. Do not need to write that down. So this is clear. So for symmetry, we assume that A is in relation to B, meaning that ABX is the same as AB inverse X is the same as XAB inverse for all elements of the group. This exactly means commuting with all elements. We need to show that this is still true if I switch the places of A and B, because then B would be in relation with A. So we need to show this here. Let's see if we can derive it from this. So I don't know how this works, so let's try. Or I've never done this before. So important here is we have this is true for all X in G. Then of course it must be true for B, X equals B, and for X equals A. Let's see if this helps us. So if I put here B, I get this. So this means that here A is B, A, B inverse. This already means that A and B themselves commute. So by simply using here X equals B, I end up with AB equals BA. Is this here something new? This would give me AB inverse A equals A squared B inverse. This doesn't look very helpful, so let's forget about this. But we know that A and B commute. Okay, I tried to use this for a while. This was not helpful at all, so let's try a different approach. We write down this here, and this can be written by the formula of the inverse of a product as this, and then again I use the formula for the inverse of a product and write it as this. All right, so I switch the order and put -1 up there, so this is the same. And now, because AB inverse commutes with all elements of X and this of G, and this clearly is an element of G, this can be written using this. This can be written as AB inverse dot X inverse. Yeah, important. This here is simply another element of G, so using this here I can switch around the order inside the parentheses. And now again I use the formula for the inverse. So I end up with X inverse inverse, which is X times AB inverse inverse. And this here is X BA inverse, again by the formula of the inverse of a product. And this is what we needed to show. All right, so B is in relation to A as well. This is interesting because usually symmetry is not hard. This here was not quite easy. And I'm not going to edit this out here because I think it's interesting for you to see that it's not always as clear as it looks in the solution. Usually, if you watch a video like that, or if you look up the solutions in a book, it's just there in one line or two, and you think, well, why couldn't I think of that? And sometimes it's really a lot of trial and error, and you have to write down some ideas, some will work, some won't, but it's not always as clear. Usually with these exercises, I already did them before, or I even thought of them myself, so I know how to do it and can write it down like that, but that's not always the case. So I think it's pretty helpful to see that it's not always as straightforward. So this is symmetry. Let's hope that transitivity is easier. Yeah, and this here, by the way, didn't help because I always have an inverse with the B or the A, so the commutation of A and B without the inverse isn't very helpful. Or maybe it is and I just didn't see it. Might also be the case. So we assume A is in relation to B, B to C. This means that these two both commute with every element of the group. Then we need to show that this is also true for the product AC inverse. Hopefully this is going to be easy. As always, we use the trick inserting the identity, in this case as B inverse B. Okay, and now, because BC inverse commutes with any group element, I can switch places here. And then again, because AB inverse commutes with every X, I can switch here, these places, and then I cancel out the B inverse and B, and I end up with XAC inverse. So AC inverse also commutes with each element of X. This is not written down perfectly. You should write down let X in G be arbitrary then, and then write down that, and then conclude that AC inverse also commutes with every element of the group. But this was comparatively easy if you have seen this trick before, which we now have done for a lot of times. Okay, I'm running low on battery again, so let's find the equivalence class of the identity real quick. So these are all group elements that are equivalent to E. So all group elements that satisfy that BE inverse commutes with all the elements, but this simply means that B commutes with all the elements. So this is simply the so-called center or centralizer. Center, I think, the center of the group, meaning all the elements that commute with all the other elements. So all the commuting elements, and this would be the equivalence class of the identity. This is exactly what we have here, not written very nicely. So all the elements that commute with all other elements. All right, let's do the final exercise, number 4. I had to trim my beard between recording sessions, so that's a clear indication that, again, this problem set is too long. Just by looking at it, I thought, well, that's a neat little problem set this time, but no, again, too long. I'm sorry. Okay, let's go through this. Proof of proposition 6. Here it is again. We have to show that a partition is nothing else than an equivalence relation in the following sense that is formulated here. So we start by taking an equivalence relation on a set A, and we define P tilde as the set of all equivalence classes. Or I could call it a family, because those are already sets. But as I've said before, we are not going to touch the problems of axiomatic set theory. So let's just say this is a set that contains these equivalence classes. This is nothing but a modulo tilde. And then we have to show that this indeed is a partition of A. So in the end we have to show that A can be written as the disjoint union of all these elements. Now, as I said in the video to proposition 6, it will often happen, or it might happen, that equivalence class of A is the same as the equivalence class of B. If there are two of the same elements in the set swallows these and makes them into one. So, for example, the set 1 and 1 is the same as the set simply containing 1. So there are no elements that can appear twice in a set. So to ease notation, we take all the distinct equivalence classes and label the representatives of these distinct equivalence classes by an index set I. So then we simply have to apply proposition 5, because if two equivalence classes are distinct, they are not the same, then they automatically must be disjoint. They can't have any element in common. So if I is not equal to j, those equivalence classes have empty intersection. This I call I, or 1. And again, by proposition 5, every element lies in one of those equivalence classes. Actually in exactly one, but that's not important. Oh well, yeah, you could say because of the exactly one also we have the disjointness, whatever. So every element of A lies in this union here of all the equivalence classes. Of course, since those are subsets of A, we also have the other inclusion, and taking both of those statements together, we end up with A is the disjoint union of the different or distinct equivalence classes. So this is exactly the condition for a partition of a set. Okay, the other way around, we start with a partition, and then we define a relation. A is in relation to B by this P here, if there is an element of this index set such that both A and B lie in the same set AI, same subset of A of this partition. And now we have to convince ourselves that this is an equivalence relation. So reflexivity. Now, because A can be written as the union of the AIs, for every A in the set, I can find an index such that A lies in AI. And trivially, A lies in AI and A lies in AI, so by definition of this relation here, A is in relation to itself. So we have reflexivity. Symmetry is equally simple, because if A lies in some AI and B lies in the same AI, then of course if I switch the order, this is trivially still true. B is in AI and A is in AI. So if I have this, which means exactly that, it follows trivially that also B is in relation to A, which means that. So symmetry is easy. Now for transitivity, let's assume A is in relation to B and B is in relation to C. Then we have to show that then A is in relation to C. So by definition, this means both A and B lie in some set AI of this partition for some index I. Same here. B lies in AJ and also C lies in AJ for some maybe other index J. But they can't be different, these indices, because B lies in AI and B lies in AJ, so B lies in the intersection. But if I were not equal to J, this intersection would be the empty set, contradicting that we have found an element in there. So this here automatically implies that I must be J. So taking this together means that all three elements lie in the same set, and in particular then A is in relation to C. So this is indeed an equivalence relation. All right, finally we have to prove that if I take the factor set of A modulo this equivalence relation that we just defined here, I simply end up with the partition itself. And in this sense, there's really no difference between a partition and an equivalence relation. Both, let's say, two sides of the same coin. All right, so we need to show that this set is equal to this set, which means they must have the same elements. So I must show that any equivalence class in this equivalence relation tilde P is of the form AI for some I, and vice versa, that every AI can be written as an equivalence class. And of course you could say, well, this is trivially true, I just defined it like that, but I would say if you're a beginner, please try to do the details and try to write them down. This might prove not as easy as you think. So let's go through it, at least the first part here we're doing in detail. So I start with such an equivalence class, and of course I can choose A. So this A here, this A I choose as a representative, because by reflexivity A clearly lies in its own equivalence class. Then, because I have partitioned the set into these AIs, I know that there is an index small I such that A lies in A sub I for some index. Small I, little I, I'm always not sure, I'm sorry. So let's take another element of this equivalence class. By definition, this means B is equivalent to A. And by definition of this equivalence relation, this means that both A and B lie in some AJ together. But then, by the same argument as above, A lies in AI, A also lies in AJ. This forces I to be equal to J. So B automatically lies in the same AI as A. And this shows that this equivalence class is a subset of this AI that I found here. The converse is also true. AI is a subset of this equivalence class. Why? Let's take any element A prime of this AI. Then of course A prime is equivalent to A. Why? They both lie in the same set AI. And this is the definition of this equivalence relation. So this means nothing but that A prime also lies in the equivalence class of this A. And if we take this and this inclusion together, we end up with this equality here. This equivalence class is the same as some AI, and this proves that this set here is a subset of this set, because every element here is one of those AIs. Okay, we're almost done. We also have to show the other direction. So we start with an AI in this partition. Then, of course, because it's a non-empty set, we can choose any element. And now we need to show that AI already is the equivalence class of this element. And this is almost exactly the same as above, and you'll forgive me if I do skip that now. And this proves in the end, please, again, if you're a beginner, write down the details. Don't just say, oh yeah, well, it's the same. There's no way around working through this kind of abstract nonsense for at least a few times in your life before you can really say, well, yeah, of course, this is somehow clear. So this proves that this set here is a subset of this set, and in the end they are equal, and this concludes the proof. Sometimes we make this line here if a proof is not complete, if we left out stuff. Here we left out a little bit, but those are not really new arguments, so I'll just put the regular end of proof box here. Whew. All right. Please, if you're a beginner and could do most of that on your own, or even if you could follow all the steps, please write a comment and I'll congratulate you. Because for a beginner, this is really a pretty high level of abstraction. Just to see what you have to prove and to actually write it down, I think this is really hard if you're not really brilliant at math. All right, that's it for problem set number 6. I promise also to myself to make a little bit shorter problem sets in the future. All right, see you in lesson number 7, hopefully.